Hello and welcome to yet another video of Cornerstones of Math. Today we will solve this simple yet beautiful problem. For each of the following cases, determine the value of a so that two curves y equals a to the power of x and y equals log base a of x are tangent. The first case is when a is greater than 1, and much less discussed but still fascinating second case is when a is between 0 and 1. Here, two curves being tangent means that both curves pass through point P and have the same tangent line, also known as common tangent line, at P. Seems like a plausible definition, so let's move on to the problem. Alright, so the first case, when a is greater than 1. In this case, both y equals a to the x and y equals log base a of x increases. But before we dive into some calculus stuff, we must first notice one important property about these two functions. These two functions are inverses of each other. And you might have learned in your pre-calculus course that if two functions are inverses of each other, then their graphs are symmetric with respect to y equals x. This means that whenever two curves touch, the point of contact always lies on the line y equals x. Due to this symmetry, this y equals x must be the common tangent line between two curves. And this will in fact make the problem significantly easier. So since the point of tangency is located on y equals x, we can write its coordinates as t, t. And now we use famous two conditions when dealing with tangent lines: the value of the function and the slope. First, the graph of y equals a to the power of x passes through the point of tangency t, t. This gives a to the power of t equals t. Next, at the point of tangency, the slope of the function y equals a to the x must be equal to the slope of the tangent line y equals x, which is 1. So first we have to take derivative. From y equals a to the power of x, its derivative is a to the power of x times ln a. If you haven't memorized the derivative of a to the x, you can always easily derive this, knowing that a can be expressed as e to the ln a. So we have this, and then we use the derivative of e to the x and chain rule. Therefore, from the slope condition, we have a to the power of t ln a equals 1. Here we can straight up eliminate this somewhat complicated a to the power of t by directly using the first equation. So we have t ln a equals 1, and this gives a equals e to the power of 1 over t. Therefore, from the first equation, t is given as a to the power of t, so this to the power of t, which is e. And if we plug this t value into here, we have a as e to the power of 1 over e, which is indeed the value greater than 1. So we have solved the first problem. And now the second case where a is greater than 0 and less than 1. Here the notable difference is that now both function decreases, meaning negative slopes throughout their domains. Therefore, although we can still convert one graph to the other by flipping it over y equals x due to the inverse relation, this y equals x definitely cannot be the common tangent line in this case. Then what would be the slope of the common tangent line in this case? Well, let's think about this way. Suppose that these two tangent lines to respective curve actually represent the single common tangent line, and these 2 points of tangency actually represent a single point of tangency on the common tangent line. This means that these 2 points are the same, and so do these two lines. But due to the inverse relation, we must be able to flip the entire thing over y equals x to obtain the other one. And the only way this is possible is like this. Here, the point of tangency is still on y equals x, but now the common tangent line is perpendicular to y equals x, which means that its slope is now minus 1. So let's use this picture to set up the equations. So this point of tangency is still on y equals x, so we can write it as t, t. Then we use the y value condition and the slope condition again. The y value condition is the same. Y equals a to the power of x passes t, t, so a to the power of t equals t. But the slope condition is now different. Here, the slope of the common tangent line is -1, so the value of the derivative at x equals t must be -1. Using the derivative y prime equals a to the x ln a, we have a to the power of t ln a now equals -1. So we eliminate a to the power of t using equation 1, which gives t ln a equals -1. So now we have a equals e to the power of -1 over t. Therefore, from the first equation, t is given as a to the power of t, so e to the power of -1 over t to the power of t, which simply gives 1 over e. Therefore, a, which is again given as e to the -1 over t, if we substitute t with 1 over e, we have e to the power of -e, or 1 over e to the power of e, which is clearly the value between 0 and 1. Now some of you still may have the hard time making sense of the second case where a has this value between 0 and 1, since in this case, two curves have a common tangent line at the point 1 over e, 1 over e, despite the fact that two curves actually intersect at that point. But remember what I said at the beginning of the video? Two curves being tangent means that both curves pass through a certain point P and have the same tangent line at that point P, which is called the common tangent line. This is the legit definition of two curves being tangent that can be found in advanced analysis or calculus text, and by this definition, whether the curves intersect or not does not matter as long as the common tangent line exists. But this leads to another burning question. We all have this vague concept about tangent which is touch but never intersect. For a single curve, a tangent line touches the curve at one point, but the line and the curve never cross over. In case of two curves being tangent, they touch, but they do not intersect. If these are all misconceptions, which they are, and thereby false, then where does this touch but never intersect concept come from? Well, it mostly comes from the classical geometry of circles, where most students are introduced to the concept of the tangent for the first time. Here we learn about the secant, which is the line that meets the circle at 2 points and definitely crossing over the circle, and the tangent, which is usually taught as the line that meets the circle at only one point, this point P. But let's think about this. What would happen in the case where this point Q approaches this point P? What would be the limit of this secant? Well, obviously, it will approach the tangent at point P. This provides the basic idea of more analytically rigorous limit-based approach to tangent lines. Consider this curve y equals fx. We want to find the tangent line at the point P, which is t, ft on the curve. If you have watched this video up to this point, you are probably familiar with the concept of derivatives. First, we consider a nearby point Q on the curve with its x-coordinate t plus h. Then we can define the difference quotient, which is ft plus h minus ft over h, which is the slope of the secant line that passes points P and Q. Then, if we take a limit where Q approaches P, which is equivalent to H approaching 0, this difference quotient may approach a certain limiting value, which we call the derivative at x equals t, and it is the slope of the tangent line at point P. In this situation, we can also think of the limit of the entire secant line PQ. This line may also approach a certain limiting line as Q approaches P. This limiting line is the tangent line at point P. That is, you can think of the tangent line as the limit of the secant line. Notice that in this approach, whether the tangent line intersects with the curve does not matter. What's important here is, just like numerous limit problems, does the limit exist? As long as that limit exists, the tangent line exists at that point. And this is the good time to take a look at the counterexample of the first misconception on tangent lines, that the tangent line cannot intersect a curve. A good counterexample of this is the tangent line of the cubic function at the inflection point, where the second derivative becomes 0, which is also the point of symmetry of the cubic function. Using whatever cubic function, you will be able to obtain this tangent line at the inflection point, which can be easily calculated by this formula. And as you can see, despite clearly being the tangent line that can be obtained by the limit of the secant line, this line intersects the curve at the inflection point, the point of tangency. So there goes our first misconception. And let us address the second misconception that when two curves are tangent, they touch each other at the point of tangency but do not cross each other. We have already covered one counterexample to this, which was our main problem about exponential and logarithmic functions. But here I will provide you one more counterexample, this time with quartic functions. Consider these two quartic functions fx and gx. Here you can easily show these relations, which basically means that two curves intersect at point 0, 1. Also, by simple calculus, you can show that both fx and gx have y equals 1 as the tangent line at the intersection point. This is of course the common tangent line. So despite having a common tangent line at the point 0, 1, two curves actually cross over each other at this point. And I guess that's all for today's video. If you managed to watch the entire length of the video, thank you very much for watching. Please go check out my other videos and don't forget to hit the like and subscribe buttons, and I will see you in another video.